My sincere greeting to one and all. I am Tamanna from BSc Chemistry on second year. Today I am here with chapter Nitro Compounds. Introduction. Nitro compounds are an important class of organic compounds which may be regarded as derived from hydrocarbons by the replacement of one or more hydrogen atom by nitro NO2 groups. Nitroarenes, for example, nitro compound in which NO2 group is directly attached to benzene ring can be prepared rather easily to and have been used as synthetic reagent since long, but nowadays even nitroalkene are being prepared and used on a large scale. Structure of nitro groups. Nitro groups is quite often represented as containing a double bond between nitrogen and one oxygen and a coordinate or dative bond between nitrogen and other oxygen. Example, N double bond O and a coordinate bond between O or N positive double bond O negative. But actually nitro compound is stabilized by resonance and is hybrid of two equivalent contributing structures given below. The resonance hybrid structure is confirmed by the fact that the bond length of each nitrogen oxygen bond is 121 picometer and or 1.21 angstrom, which is intermediate between NO single bond length 136 picometer or 1.36 angstrom or N double bond O double bond length is 115 picometer or 1.15 angstrom. In case of nitroarenes, resonance of nitro group with the ring can also take place, giving rise to additional contribution structure of the molecule. It will be interesting to note that nitro group is isoelectronic with carboxylate ions. Nomenclature of nitro compounds. Nitro compounds are named by writing the word nitro before the names of a parent compound. The number of nitro group and their position are also stably indicated as illustrated below. Nitromethane, nitroethane, 2-nitropropane, 2-nitro-3-methyl-butane. Nitrobenzene, orthonitrotoluene or 2-nitrotoluene, meta-dinitrobenzene or 1,3-dinitrobenzene, para-nitrobenzene or 4,4-nitrophenol. Classification of nitroalkenes. Nitroalkenes are termed as primary, secondary or tertiary according to the nitro group is attached tertiary according as the nitro group is attached to a primary, secondary or tertiary carbon atom, that is primary nitroalkane, secondary nitroalkane, tertiary nitroalkane. For example, nitroethane, 2-nitropropane, 3-methyl 2-nitropropane. Preparation of nitro compounds. Preparation of nitroalkenes. Nitroalkenes are usually prepared by the following method. First is vapor phase nitration of alkene. The reaction involves the substitution of a hydrogen atom of the alkane by a nitro group. It is carried out in the vapor state by heating the alkane with nitric acid about 700 Kelvin temperature. Limitation of the process. During nitration of higher alkanes, all possible isomeric nitro products are formed. Moreover, repurchase of carbon-carbon bonds also take place, leading to the formation of nitroalkanes containing lesser number of carbon atoms. For example, nitration of propane results in the formation of a mixture of 4 nitro compounds as shown below. Propane nitration in presence of HNO3 at 373 Kelvin temperature give first nitropropane, 1-nitropropane 25%, 2-nitropropane 40%, nitroethane 10% plus nitromethane 25%. Due to the formation of complex mixture of product, this method is not used for laboratory preparation of nitroalkenes. However, the method is widely used for the commercial preparation of nitroalkenes since they are used as industrial solvent only. Mechanism. The reaction is believed to involve the formation of free radical, but the mechanism is not well established. Second, action of silver nitrate on alkyl halide. This is the method generally employed for the laboratory preparation of nitroalkenes. When heated with silver nitrate, alkyl halide undergo nucleophilic substitution to form nitroalkenes along with small quantities of alkyl nitrates, RONO double bond O. This is because NO2 negative is an ambidextrous nucleophile. However, the mixture of alkyl nitrate and nitroalkane can be separated by fractional distillation mechanism. Third, oxidation of amines. When a amine in which the amino nitro is attached to the tertiary carbon atom is oxidized with potassium permanganate, a tertiary nitroalkane is observed. Preparation of nitroarenes. Nitroarenes are almost invariably prepared by direct nitration of arenes. The nitrating agent are generally used as concentrated or fumic nitric acid. Second, mixture of concentrated or fumic nitric acid and concentrated sulfuric acid. Sometimes fuming sulfuric acid is also used. The mixture is most commonly used as nitrating agent. Third, mixture of concentrated nitric acid and acetic anhydride or boron trifluoride. Fourth, acetyl nitrate CH3COONO2 obtained by mixing nitrogen pentoxide and acetic anhydride. Fifth, nitrogen peroxide in the presence of anhydrous aluminum chloride. Choice of nitrating agent. The choice of nitrating agent to be used for nitration of a given compound depend upon the following two factors. First, nature of compound to be nitrated. Second, number of nitro groups to be introduced. In the nitration of aromatic compound containing electron releasing or activating group such as NH2OH CH3, the reaction takes place readily at room temperature by employing concentrated HNO3. In cases even dilute HNO3 can be used. For example, phenol plus dilute HNO3 gives ortho or para nitrophenols plus H2O. For nitrating compounds containing electron attracting or deactivating groups such as COOH, or when it is desired to introduce more than one nitro group, a suitably strong nitrating mixture has to be employed and the reaction is carried out at high temperature. It may be remembered that nitro group itself is also a deactivating group. Nitrobenzene is and meta-nitrobenzene, for instance, can be obtained from benzene under the conditions shown below. Benzene gives meta-dinitrobenzene in presence of concentrated HNO3 and concentrated H2SO4, and benzene gives nitrobenzene with the presence of concentrated HNO3 and concentrated H2SO4. The difference is between the temperature. Mechanism of nitration. Nitration of aromatic compound, like other aromatic substitution reaction, is electrophilic in nature and involve a nitronium ion NO2 positive as the attacking electrophile. The mechanism may be summed up as follows by considering the nitration of benzene with nitric acid sulfuric acid mixture. First generation of electrophile HONO2 plus H2SO4 gives nitronium ion. Second is the formation of carbocation as shown below, and third is proton transfer from the carbocation to yield the final product. Evidence in favor of the above mechanism. It has been shown above that aromatic nitration involves a stepwise mechanism. The nitronium ion, which act as the electrophile reagent, is generated in a preliminary step and bring about further reaction in two steps. The first step is a slow rate determining step, involve the addition of nitronium ion to the aromatic ring to form a carbocation intermediate. The second step, which is relatively fast, involving the elimination of a proton from the intermediate ion by the heterolytic cleavage of CH bond. First, C6H6 plus NO2 positive gives C6H5H NO2 slow. Second is the fast reaction. The mechanism has been fully supported by isotope tracer technique as explained below. If an aromatic compound labeled with deuterium, the heavier isotope of the hydrogen having a mass of 2 AMU, is subjected to nitration, it is found that the rate of substitution of deuterium is same as that of ordinary hydrogen or plutonium. In other words, no isotope effect is observed, since Nitrobenzene of melting point 278.8 Kelvin and boiling point 463 Kelvin. Dinitrobenzene has melting point 363 and boiling point 576 Kelvin. 135 Trinitrobenzene has melting point 395 Kelvin. Chemical reactions of nitroalkenes. The important chemical reactions of nitroalkenes are as follows. First, acidic nature. Tautomerism. Nitroalkenes containing alpha hydrogen atom, example primary and secondary nitroalkenes only, exhibit acidic behavior and form salt in presence of strong alkyne. The acidity can be attributed to the fact that first, nitro groups have a strong electron withdrawing inactive effect, psi effect. Second, the anion formed after the removal of the proton from nitroalkene get resonance stabilized due to the ability of a nitro group to accommodate negative charge as shown below. It is interesting to note that if the salt formed by nitroalkane is acidified at low temperature, the oily drops of nitroalkanes do not separate immediately, but we get another form of nitroalkanes known as acenitroforms, which slowly changes into nitroform. This is due to the fact that primary and secondary nitroalkanes exhibit tautomerism, the tautomeric form being nitro or iso form and acenitro or nitroic acid form. The tautomeric equilibrium between the two forms lie about completely toward the nitro group because it is stabilized by the resonance of nitro group. Acenitro forms a relatively stronger acid than nitro form. An important feature of acid nitro form is that it can act both as an electrophile and a nucleophile. Unlike primary and secondary nitroalkanes, tertiary nitroalkanes and nitroarenes do not have any alpha hydrogen atom. As such, they exhibit neither acidic character nor tautomerism. Third, reduction of nitroalkanes. Reduction of nitro compounds is one of their most important reactions. The reduction of nitro group takes place in stage as shown below. Nitro compound gives nitroso compound, gives substituted hydroxyl amine, and then give primary amine. The product actually obtained depend upon the nature of the reducing agent and the pH of the reaction medium. Thus, nitroalkanes can form different products on reduction as given below. First, reduction in acidic medium. When reduced in an acidic solution, nitroalkanes form primary amines. Nitroalkanes plus 6 H molecules in presence of FeHCl gives primary amine plus H2O, get 2 molecules. Second, catalytic reduction or reduction with LiAlH4. Reduction with LiAlH4 or H2 in presence of nickel, palladium or platinum catalyst also yield the same product. Reduction in neutral medium. If the reduction is take place in neutral solution, a hydroxylamine derivative is obtained. The hydroxyl amines are readily oxidized to corresponding nitroso compound. On warming with Tolvin's reagent get reduced to the metallic silver. This reaction is used as a test for nitro compound under the name Baker-Mulliken test. Third, hydrolysis. When boiled with concentrated HCl or H2SO4, primary nitroalkanes undergo hydrolysis to form carboxylic acid and the corresponding salt of hydroxylamine. For example, nitroalkene primary in presence of H plus H2O plus HCl in presence of heat gives RCOOH and NH2OH HCl and so on. Secondary nitroalkenes are hydrolyzed to ketone and nitrous oxide by boiling with concentrated HCl. Tertiary nitroalkenes or nitroarenes are not hydrolyzed by acid. Fourth, NAF reaction. When sodium salt of primary and secondary nitroalkenes are hydrolyzed by boiling with dilute sulfuric acid, aldehyde, and ketone respectively are obtained. The reaction proceeds through the acne-nitro form of nitroalkenes. For example, sodium salt of primary nitroalkanes correspond to aciform plus H2SO4 gives aldehyde plus 2NaHSO4 plus N2O plus H2O. Sodium salt of secondary nitroalkane correspond to acid plus 2 mol of H2SO4 gives ketones. In this reaction, the acid nitroforms act as an electrophile. Fifth, action with nitrous acid. Primary, secondary, and tertiary nitroalkenes exhibit different behavior toward nitrous acid. First, primary nitroalkenes react with nitrous acid to form nitrolic acid, which dissolve in NaOH to produce a red solution. Nitroalkenes gives nitrolic acid dissolved in NaOH to give red color due to the formation of sodium salt. Second, secondary nitroalkene react with nitrous acid to form pseudonitrols which have blue color but do not dissolve in NaOH. Third, tertiary nitroalkanes and nitroarenes do not react with nitrous acid since they do not contain any alpha hydrogen atom. The above reaction can be used for distinguishing between primary, secondary, and tertiary nitro compounds. Halogenation. When treated with halogen, chlorine, or bromine in slightly alkyl medium solution, primary and secondary nitroalkanes undergo halogenation at alpha position. For example, nitroethane 1 chloronitroethane 1 dichloronitroethane 2 nitropropane in presence of Br2 NaOH gives 2 bromo 2 nitropropane. The mechanism may be summed up as nitrobenzene, then free radical anion, then nitrobenzene, free radical anion, and second, catalytic reduction. Reduction of nitrobenzene with H2 in presence of nickel or platinum catalyst also lead to the formation of aniline. Third, reduction in neutral medium. When reduced in neutral medium, example with zinc dust and ammonium chloride solution, the reaction stop at the hydroxylamine stage. Refer to the mechanism given above. Phenol gives in presence of Zn aqueous NH4 Cl2 gives benzene NHOH H2O. Fourth, reduction in alkaline medium. On reduction in alkaline medium, nitrobenzene yield different products depending upon the nature of the reducing agent employed. These products are actually formed by further reaction between the primary reduction product, example nitrosobenzene and phenyl hydroxylamine as shown given below. Azoxobenzene A is formed by condensation of nitrosobenzene and phenyl hydroxylamine as given below. This is sufficient evidence to show that azobenzene B is formed through the intermediate formation of azoxobenzene and its further reduction. Hydrazobenzene C is similarly formed by the further reduction of azobenzene. Fifth, reduction with LiAlH4. Reduction of nitrobenzene with LiAlH4 also yield azobenzene. Sixth, electrolytic reduction. When reduced electrolytically in weakly acidic medium, nitrobenzene gives aniline, but on electrolytic reduction in strongly acidic medium, nitrobenzene yield para-aminophenone due to the rearrangement of phenyl hydroxylamine first formed. Electrolytic reduction in alkaline medium yield hexoxobenzene, azobenzene, and hydrazobenzene. Seventh, selective reduction. In case of compounds containing more than one nitro group, it is possible to carry out the selective reduction in one of the groups by employing a mild reducing agent such as ammonium hydrosulfide or sodium polysulfide. For example, meta-nitrobenzene plus 3NH4SH gives meta-nitroaniline plus 3S plus 2H2O plus 3NH2. This is known as xenon reduction. Third, electrophilic substitution. Nitro groups, being an electron withdrawing group, have a strongly deactivating effect on electrophilic substitution reaction of benzene nucleus. However, under the strong condition, nitro compounds may undergo electrophilic substitution in meta position with respect to nitro group. For example, metachloronitrobenzene is formed from nitrobenzene in presence of Cl2 FeCl3. Nitrobenzene in presence of fuming H2SO4 gives meta-nitrobenzene sulfonic acid, and nitrobenzene in presence of fuming HNO2 and HNO3 and concentrated H2SO4 give meta-dinitrobenzene. It may be noted that nitrobenzene also does not undergo Friedel-Crafts reaction. Fourth, nucleophilic substitution reactions. The nitro group has no doubt of a deactivating influence on electrophilic substitution in benzene nucleus due to its electron withdrawing nature, but this is very electron withdrawing influence on the nitro group makes the benzene nucleus liable to be attacked by electrophilic reagent. Thus, unlike benzene, nitrobenzene in heating with sodium hydroxide gives small amount of ortho and para-nitrophenol. The mechanism of the reaction may be outlined as following consideration from the para-nitrophenol. Fifth, placement of nitro group. In case of polynitro compounds, one of the nitro group itself can be placed by nucleophilic group. For example, para-dinitrobenzene in presence of 2 moles of NH3 gives para-nitroaniline plus N2 plus 2H2O. In presence of KOH gives para-nitrophenol plus KNO2. In presence of C2H5ONA gives para-nitrophenol plus NaNO2. Thank you.